or evening as the case may be. I'm Scott Holloway and welcome to another edition of Holloway Help. Today's topic is springs. Okay, so we're talking about springs. And the springs we're going to deal with in AP Physics are primarily ideal springs. We will have some that are non-ideal, but we're going to talk about ideal springs first. The one thing we assume, which is completely wrong, is that the springs have no mass. That makes the calculations much more straightforward and simple for us to do. So when we look at a spring, one of the important concepts is that the force a spring exerts, F sub s, is going to be proportional to the displacement of the end of the spring. In other words, how much it's stretched or compressed. We usually multiply it by a spring constant, hence proportional, directly proportional, linear proportionality between the stretch and the force. The negative sign indicates opposite direction. So if I stretch a spring out to the right, it pulls back to the left. The force is opposite direction of movement. So this is a position vector, if you will, like so. Now, for an ideal spring, it obeys this law, that the stretch is proportional to the force. And if it is, we say that's a Hooke's law spring. Also known as an ideal spring. If you have a spring scale, the spring in the spring scale is an ideal spring. So that when you place a weight on the end of it, the markings are linear. In other words, there's an equal gradation between each marking. So each additional stretch is going to be an increase in force required to stretch the spring. So when you put a mass on there, you can tell the weight by using gradations. So a spring scale is an example of an ideal spring. And this is sometimes what they'll use in the case of an AP question to measure the tension or the pull. Spring scales cannot measure compression, or a standard one does not. They have some that do. But usually they have it to measure the tension in the string. When we look at an individual spring, and we hang a mass on it, if you let the mass go, you're going to get an oscillation. It's going to bounce up and down, and we'll talk about oscillations. Now, ideal spring would oscillate up and down forever. Here, I'm not holding my hand very still. The hand's bouncing as well. But a little bit of friction and air resistance will bleed out or dampen the oscillation to bring it to a standstill eventually. If I put this on a ring stand, hook it up, and then let it oscillate, it'll actually bounce a little better for a little longer. The first thing we're going to look at, though, is if we let it come to rest, we notice that the spring is stretched longer than its original length. So here's its original length, here's its stretched length at rest. So we're going to do a free body diagram on the mass and look at what's happening to the mass. So we have our mass, it's stretched the spring. There's a symbol for a wall or a ceiling, is a line with little hash marks along it to represent a solid object that's not going to move. The spring's attached to that, it's attached to our mass of M. And the original length here, we call that the original length, and then our new length here, this is going to be from here to here, a distance of x. It's how much it's stretched. So when we do our free body diagram on the mass, we've got the spring pulling up with F of s, and of course we have mg down. Next step after doing a free body diagram is typically to do some of the forces. I'll do that down here. Some of the forces in the y direction equal ma sub y. Now looking at the block, it wasn't moving, it was sitting still, so a in the y direction is 0, so that all the forces are going to add up to 0. So we plug in our forces. We have F of s positive minus mg, because it's down, equals 0, or F of s equals mg. Now I'm going to erase and move up so you can see this a little better. All right, we got to F sub s is equal to mg. Now our original statement was that S of s is negative kx if it's an ideal spring, and the spring I was using was an ideal spring. So that means negative kx is equal to mg. Or, if we divide x from both sides, or negative x, the spring constant, K sub s, if I put the little sub s, sometimes my K's look like a capital K and get confused with kinetic energy, so I like to use the K sub s to remind myself it's spring constant. K sub s is given by the weight on the end divided by the stretch from the original length of the spring. So how much did it stretch downward? And this gives us our spring constant. So K is a spring constant. Elastic constant, it may also be written as, and it's going to be given in newtons per meter because it's weight over distance. So newtons per meter is going to be the unit for that. So that's how you calculate the spring constant. Now that we have the spring constant, we can use that in other calculations. So our basic equation, F sub s is negative kx, is useful for finding how strong is a spring pulling when it's being stretched. If we look at a horizontally mounted spring, so this is my wall, I attach a spring to it, and I put it on a frictionless surface, mu is 0, and I attach a block of mass m. So this is what we call our equilibrium point, our starting position. The spring is neither compressed nor stretched. It is in its relaxed position, so it's just sitting still, the block is going nowhere. I grab the block and I slide it out to a new position. And we call this x, or a for amplitude. So if I stretch out that way, when I'm holding it here, the spring is now stretched further. So at this point, the spring is going to want to pull back. So here, F is going to equal negative kx. The strength of the pull will be equal to how far we stretched it times the spring constant, which we could solve for using the equation we just saw. The acceleration, the block, if I let go of it, the acceleration is simply going to be F over the mass of the block, which will be negative kx over m. Now, if I let go of it here, what will happen is it'll move, it'll accelerate all the way to this point, which means it's going to be picking up speed, picking up speed. When it gets to this point, after it passes, it's going to start compressing, so it'll start slowing down over here. But right here, it was accelerating all the way to this point. So this is going to be my maximum speed. So at this point, at equilibrium position, your velocity is a max. It's very important that you remember this because it helps you solve a lot of problems with springs. So velocity is a maximum here, and if velocity is a max, kinetic energy, capital K, is also a max. All right? The block will continue to move back this way and will travel to a position over here of negative x. It'll be whatever we stretched out. If the spring has room to do it, it'll come back negative x the opposite direction. And these will be mirror images of each other. You'll have the exact same F equals negative kx, which means your force is going to be a maximum at this position and this position. These are your maximum force because the most the spring was stretched for this instance. Acceleration is a maximum. And when force is a maximum and the distance is a maximum, force times distance, remember, was work. Work is energy. Energy stored in the spring is going to be a maximum, and that's going to be U sub s. We'll talk about that in a minute. But the potential energy stored in the spring, U sub s, is also maximum at this position. So we have maximum force, maximum acceleration, maximum potential energy. Keep those in mind. They all go together, and those are at the ends of the stretch, the maximum stretch. Where this point happens, if it's oscillating back and forth, when it gets to this point, it's the turnaround point. So it slows down, velocity goes to 0, which means the kinetic energy also goes to 0. So you have the minimums for velocity and kinetic energy at the end points, maximums here in the middle. So equilibrium point, maximum kinetic energy, maximum velocity. And then what would be our force here if we have no stretch? F times kx, x is 0, times anything is going to be 0. So here your force is 0. Acceleration we know is force over mass. So acceleration has to be 0 at this point. Very important you remember that for equilibrium. A is 0.